and share my screen. Should be able to see my screen.
We see it.
Cool. Welcome everyone. This is our fourth coding adventure in TensorFlow. My name is George Soto, and I'm joined today by great friends, especially my two best friends and co-organizers, David and Robert. Today we're going to talk about structured data set and how do we detect fraud in credit card transactions. If this is the first time you're joining us, welcome. If you found us through YouTube or Meetup, again, welcome. I wish we had some extra time in the end to get to know everybody, but today's going to be an action-packed session. I want to reserve all the time we have going through the different notebooks that we have put together. Again, if this is the first time you joined us, we've been going on a 5-week coding challenge with TensorFlow. We covered a computer vision problem, detecting diseases in cassava plants. Then we tackled an annotation problem in NLP with the Big Bang Theory, the data set behind a few scenes behind the popular TV show. Then we explored a larger data set for friends, where we looked at classifying emotions for the different episodes and different sentences, and whoever was in different actors were trying to detect one of 7 emotions. Today is the 4th challenge out of the 5-week challenge that we've embarked on, and today we'll be talking about structured data set. Just a few updates or reminders. Again, we have if you came to us from a different channel, on Meetup, you can find us if you search for Deep Learning Adventures, as well as on YouTube. We have links here for our recorded sessions, as well as a new playlist for the coding sessions. Just a thank you to Machine Learning Paper Club for cross-posting this event, as well as Bethesda AI Meetup for cross-posting it as well. And Data Education DC and Upskill ML to create partner meetups that aim to promote data science and AI in the DMV area. As well as Hashpad, they cross-posted some of our events, actually all of our events in their larger network. They work with startups, as well as they interview companies nearby, so you get to know what is the culture like, what kind of technology stack they use, so that if you're interested in joining them, you have more of like an insider's view. Cool. We won't have time to say hello and get to know everybody. I'm amazed at the number of members that have joined us over the last couple of weeks. Hopefully we can cross the 1,000 pretty soon. And again, welcome everyone. I'm not sure we're using any in this session Coursera Deep Learning AI. This is just a slide to pay attribution to them in case we do. And in terms of frameworks, we'll be using TensorFlow, an open source machine learning platform where you can tackle NLP, computer vision, structured data set, as we'll see today, as well as time series challenges. For setup, you don't need anything super expensive or super hard to get. We've been using Colab, which is a free Jupyter notebook hosted on Google Cloud Platform. All you need is a Google account, and you can set up a new account here, and you can access CPU, TPU, or GPU instances for free. Cool. So as I said, we tackled the computer vision, an annotation challenge, and an NLP challenge, and today we'll be tackling the structured dataset challenge. I highly encourage you to also join us for the 5th and final coding session, which is a couple of weeks on time series prediction. We'll be using weather data there to predict weather, maybe a week, a month, and so forth. Cool. I'm going to skip the slides. I shared them on the Meetup. I also shared them on Slack. Please join us on Slack. You can find our Slack on our Meetup. And when I get a chance, I'll also post it on Zoom. So I'll go right here. There were some great notebooks that many of us put together. I just put some slides here, but the goal is really to go into details, into the coding approach and how we tackle this. These are just some slides to motivate us, to get our appetite for what we're about to see. So Dimitri put a great notebook. Hopefully we'll have some time for him to explain to us his approach. And David as well put an excellent notebook, Robert as well. And I'm still working on mine, very simple notebook on my end, and all the links are shared there. Having said that, I'd like to hand it over to Robert to guide us through this data set and his approach as well. So Robert, I'm making you host so you can share your screen.
Answered my question before I asked it.
Yeah. You should be able to know.
Great, let me find my notebook. Share screen. Can you see my IPython notebook?
Yes.
All right, so for those who have not yet embarked on this challenge, I'll just lay out the problem a little bit. We are looking at a data set which is entirely contained within a CSV file, creditcard.csv off of Kaggle. And what we agreed early in the challenge was, given that this particular data set had no splits, train, test, validation, we decided that we would carve out a standard set so that all of us could test against the same test set. So David provided the one line of code here to train, test, split df to do that conversion. And I've replaced the first element of the target with the TV df training and val. Eventually down here in this particular cell, I'm just getting separate data frames for train, val, test, and train val for X and Y. This data set, as you can see, well, I don't think I actually showed the whole thing, but look at the describe anyway. It's 227,000 points once you've removed 20% of them for testing. And there's a time field, a whole bunch of features labeled V with a number after them, an amount, and a class. And the amount is a dollar amount of a transaction. The time is the time of day, or the time in seconds elapsed since the beginning of the data set. And this is 2 days, 48 hours worth of transactions. And the location, if I recall correctly, is somewhere in Europe. And the other features, which are somewhat mysterious, are these V's with a number after them. And they are actually the results of a principal component reduction on an initial data set so that we have the features masked from us. We don't know what the physical or economic or whatever meaning of these is. All we have is these black box features to work with. They're all numeric. Every single one of these things is numeric, but obviously there's different scales. We have time in seconds, amount in dollars, and some kind of standard units for these principal components. One thing you can see by looking through the standard deviations is that the standard deviations are decreasing, which is the typical case for principal components. The means are not exactly zero here, but the reason for that is because we have taken the test set off. I actually went and verified to make sure that the means are exactly zero of these principal components when the test set is included. So it seems reasonable to assume that it actually is a principal components breakdown. I think they, on Kaggle, indicate that it's likely they're principal components, but possibly not confirmed. So just started with a really basic exploration, looked at some of the class distribution and you saw that some features, the means of the few fraud points, were well out of the legit points. I think I should probably have described the severe imbalance in the data by now. So of our 220 some thousand points, only 400 of them are fraud in the train val test set, in the train val set. On the original file, we had 492 fraud points. 98 of those were scurried away into the test set. 78 of them are in the val set, and I believe there's roughly 320 in the remaining training set. So some of the features look strongly separated, other ones do not. When we get to, if Dimitri presents his notebook tonight, you'll see some violin plots here, which really illustrate this in a much easier way to see. But I've got a few of my own visualizations here just to show. So the time field, as you can see, these are plotted with respect to the index in the database and data set. So everything is sorted according to time. If we look at V1, we have, I coded the fraud points as red and the background as black. So our principal component 1 shows us a couple of interesting things here. We've got some clusters here of fraud. You can see a few strings of it that all happen to occur around the same time. This could be one individual or organization that is attempting to commit multiple transactions fraudulently all at the same time. Interesting to note that these two sprees, and actually all 3 of them I would say, are probably in off hours. This one's probably a little bit after midnight, this one's a little bit after midnight, and this one may be in the really early morning. But the bulk of the transactions occurred more in here and in there. And that is masked by this particular visualization. So one of the features that did a decent job of separating was the V14. So here's a plot with the index in the data set on this side, which is kind of a surrogate for time, if you will. And the V14 feature here, we can see that definitely these outliers with the high negative values are likely to be fraud points. And we do have a few other fraud points that don't separate themselves too well for this one feature. And notably, there are no fraud points with high values of V14. And just to look at the amount, this is a transformed visualization of the amount. Essentially, this is looking at the log base 10 of the amount so that the points here at 0 are $1 transactions, -1 are 10-cent transactions, -2 are 1-cent transactions. And for visualization purposes, I coded it so that the ones with 0 cents show up here at -3. High dollar transactions are up top. And you can see there's not really anything obvious about what's fraud here. Looks like there may be a number of fraud points hanging right around exactly $1, but not clear what we can do with that.
Robert, I was going to ask you if you thought about eliminating the 1s and 0s, because as somebody who worked in the credit industry, when you're doing PCA tests, you run $1 transactions, and since they're not on a real account, they would trigger as fraud.
Interesting. I didn't know that. I wonder if that is the explanation for some of these ones here that are right along this 0 line. They do seem to occur, at least this bunch and that bunch are at times that are in the middle of the night. So I don't know what that tells us.
Are you talking about the temporary transactions, like when you subscribe for something, you get charged for like $1, Stephen?
No, what I'm saying is if you're developing a system and you have to demonstrate what's called PCA compliance, which just means you have the security features in. So you run $1 transactions, but the payment agency is not going to give you a live account because then they would have to run it through their books.
Mm-hmm.
So they give you an account that will work, but won't show as valid. You see, so they'll reject them. And then, so I think the analysis is good. I was just going to ask about how much you looked at, you know, the flagged fraud cases, because I ran a count and there were like 500 ones and a few zeros. And again, those may be indicative of testing.
Could be, yeah. I don't remember anything about testing in the Kaggle dataset description. That's interesting.
Yeah, I was unaware of that reason for there being single dollar transactions. So I didn't really think about it much beyond looking at this and determining that they didn't seem too separable.
Mm-hmm.
Based on
and there were also some in there. There's a good number that are in there for exactly 99 cents. And those are used by audit to test edge conditions.
Well, those could be right there at 0 as well. I didn't drill down to see exactly what that number is. But this is a log-based 10 of the amount.
Question for you, Robert. You mentioned V14. We'll see that V14 pretty soon in other notebooks. How did you decide to go with that and that feature? How did you decide it was so important?
So I suppose I didn't necessarily do everything in here in the order that I'm presenting it, but to get to that point, when I plotted the cumulative distribution function of the fraud points in V14 versus the backgrounds, this one seemed pretty well separated on its own.
Got it. Okay, something to keep in mind.
Right. So this is just to summarize in case cumulative distribution function is new to anyone. The value on the vertical axis here is what fraction of points lie below any given value. So with a value on the x-axis of -5, a very small fraction of legitimate transactions have a V14 below -5. But if we come up here, we see that maybe over 60% of our fraudulent transactions have a V14 of -5. So it's just a different way of visualizing class separation, which can be useful.
Nice. So
I wrote a little routine here to plot the CDFs. This was also a like plot imbalance series. Wrote a little routine to do that. So I was able to kind of rapidly look at each of the different features and decided that V14 and V17 looked like the two that if you had to rely on a single feature, they look like they might be the two most useful.
Cool.
So let's see. I guess I just described the CDF and definition of that. Did a little bit of bivariate and correlation calculation as well. This is a visualization of two of the features that did not distinguish themselves very well. So we have scatter two fields, imbalanced, V22 and V15, and the fraud points all kind of cluster inside the box where most of the background transactions lay as well. So some of these features in the principal components don't seem like they might be too useful on their own. Others do. Here's a visualization similarly looking at the two that seem like they had the highest disparity. So this is V14 scatter plotted against V17. And this, well, it's a little bit of interesting structure in this data set here. Perhaps these lines out here are related to some of those clusters that we saw back in this plot here. We have a line of legitimate transactions there and a few different clusters of fraudulent transactions, all with outlying V14s. And it looks like the V17, for these ones at least, might correlate fairly well. And this is also looking at V14 against this logarithmic view of the amount. Time against amount. So just for my own edification, went back and computed the correlation on the original data frame, verified that all the off-diagonal elements here are essentially 0. When I ran this same correlation on the main data set, you tended to get values around 10 to the minus 3, 10 to the minus 4. So moving on to a couple of really simple kind of first stab, what is the simplest?
Robert?
Yeah.
I have a quick question. Sorry to interrupt, but as far as correlations, does it matter whether you're looking at these with an imbalanced versus a balanced data set? Like, are these correlations likely to be only correlations with the majority class? Or
Well, the majority class, as we know, is 99.83% of the samples.
right?
So yes, the majority class certainly dominates. Because the PCA were taken of the full data set, including the fraud and the background, with the actual class balance, it too is weighted towards the majority class.
Okay.
So I said, you know, let's just take a very first stab at this and not build any real model at all, but just like try to use the V14 directly as a confidence value, see how that does under our metric AUPRC, and we'll consider that the baseline. So decided to convert it through min-max scaling into essentially a confidence value. So this is just another view on V14 where I've converted the minimum. Remember, it actually had negative values where the fraud was. So the minimum of V14 has been mapped up here to +1. Maximum of V14 has been mapped to 0. And we're just going to use these as confidence values and build a precision recall curve straight off of this. Before, I guess the notebook shows scikit-learn pipelines here as well. I built a little transformer amount transformer that inherits from the base estimator and transformer mix-in classes. These are really useful devices to design your own pipelines in a way that allows you to just feed in data and not have to worry too much about pre-processing when you are predicting subsequently after training. So for this particular one, I anticipated wanting to do some kind of a logarithmic transformation on the amount. Otherwise, the rest of the columns, I think, will just be standard scaling. So mean and standard deviation based normalization. And created a simple pipeline out of this. Well, no, this first one, pipe 1, is just to check whether the pipeline's working. Pipe 2 is where we actually run so I ran it as if it were a logistic regression, but really it's a logistic regression of a single variable. And the logistic regression is just going to produce an affine transformation. So essentially it is using the V14 as its metric for sorting the data. And we can verify that by plotting the decision function the class that it decided to put something in versus the confidence in some coordinate system here. So this is V14 basically separated. And another way of visualizing that is down here. And this is that same view of V14, but now we have coded, instead of just black and red, the samples which have been predicted positive are coded as blue if they are false positives and yellow if they are true positives. And this is just a way of verifying that, yeah, the classifier is performing exactly as expected, where it's just taking this one feature and slicing it right here. All the black and red points are above this line. All the blue and yellow points are below it. Viewing the cumulative distribution function, same deal. Here's our threshold. Did a little bit of looking at confusion matrix, but the point of this was to get a baseline precision recall curve, and that's what we see here. And used the AUC function imported from scikit-learn metrics, from sklearn metrics, import AUC. And that computes an AUC for the validation set of 0.668. And scikit-learn documentation shows that there's multiple ways of computing it. There's actually an average precision score, which is essentially the same thing, but they do the integrals with slightly different approximations. And the documentation shows that the one labeled AUC is probably a better approximation. Average precision score is likely to overcount. I think it's basically doing Riemann sums, maybe, where it's taking a slightly overly optimistic as it's decreasing. So for the rest of the notebook, I'll just use AUC. So with that in hand and a baseline validation performance of around 0.67, decided to fit a full logistic regression model using all the features with this transformation where the amount was transformed, everything else was scaled, standard scaling. Logistic regression started with no penalty, no regularization. Now we see that there's some mixing when we plot just against V14, so it's using something other than just this single feature. And the precision recall curve, now the previous one is the black one and the new one is the blue one. So we're doing a lot better when we use all the features, and validation performance is now up around 0.8. So surprising, not too bad, with really very little tuning on the logistic regression model, getting about 0.8 on the val set.
Question, Robert, can you tell how many features you're using when you do this model?
I'm sorry, can you say that again?
Can you tell how many features you are using as input?
So, I mean, so you can actually extract out the function. Now, because there's no regularization, it's going to actually use all the features as opposed to something like L1 that would cancel out some of them. Mm-hmm. But certainly some of them will have much higher coefficients than other ones. Right. I didn't look at it.
Just to clarify my understanding, the first curve is using only V14 and the blue one is using all features as input?
Correct.
Okay, thank you.
And because it's a logistic regression, it is enforcing that the decision boundary in the feature space will be linear, will be a hyperplane. But it is using all the features.
Cool.
So I tried a couple different penalty options. I think I only show one here, played around with it a little bit. I didn't get a whole lot of improvement from changing the penalty. A couple things, maybe the highest one I got was around 0.803 instead of 0.800. So didn't really try any further on that. Decided to start looking at random forests. So random forest is a tree-based model that introduces randomness into decision trees in two different places. One, it does a bootstrap sampling on the data set, so it will pick a different mix of points each time to feed to a tree. And the other source of randomness is that each tree is only allowed to consider a subset of the features. And I just stuck with the defaults here. I wasn't interested in tuning it too excessively. I believe the default is that the number of features is about 1/3 of the total number of features. So with roughly 30 features, the default here would be that each tree can consider about 10 of them. So we again fitted this into our pipeline structure. Now, since it's a tree-based model, actually, there's really no need for these transformations that I had done previously. No need to do logarithmic transformations on the amount, no need to do standard scaling. The tree-based model is really just looking for points where it can make splits, and the numerical values of these points really don't matter at all. Only in regards to where they sort the points. So it simplifies the pipeline generation. The function predict probabilities after one trains with the fit allows you to take the validation set and produce predictions. And it actually does so for each of the two classes. So I'm just going to look at the fraud class, which is 1.
So if you don't mind, if you're not unmuted, do you mind muting yourself? We hear some feedback. I'm not able to find where it's coming from.
So out of 45,000 validation points, this first model predicts 1,100 of them as class fraud, which is much higher than the total amount, but that's fine. All we're really looking at is the AUPRC. So because of that, we're just going to run with what we have. So this particular, I guess when I upload it to GitHub, this doesn't condense this. We'll have to skip down through a long list of numbers. Just checking to see where our predictions lie. The vast majority of them are very close to 0.
Sorry, Robert, do you mind, since you're the host, do you mind muting people? I'm not able to mute them.
Sure. Let me.
Participants, SKCL and Rajat.
Does that help?
Yeah.
Yeah. Okay. I think that was it.
Thank you. Thank you, friends, for identifying outliers.
Sure. Sorry, I had totally forgotten that I was the host, and I guess I would be the only way of doing it. So I guess the only reason that I printed this out was, 1, to look at the distribution, but 2, to just illustrate the way these random forest models work. With 100 trees, what's happening is each one of the trees is voting. Is it a fraud point? Is it not? So the confidences then are just the fraction of trees that are voting for yes, which is why the confidences here in the left column end up, when you have 100 trees, every one of them is just a no more than 2 decimal places. So they're discretized to some extent. Looking at the confidences overall, yeah, it's very imbalanced, but we have enough variety here that we can produce a precision recall curve off of it. And I just built that using the precision recall curve function and then plotted it here. And our AUC against our validation set here is 0.873. Not too bad. So tried a number of things, adding more trees, adding 1,000 trees. Now we get a 3rd decimal place. Not really much difference. One thing, it seems to lower the confidence up here. So there's some trees now that are voting not fraud, even for points that are pretty clearly fraud. But at the same time, it's raising the number of fraud points nominated in this region down here, which is actually possibly quite useful, depending on the company that's using this and how many transactions they want to investigate. When you think about what this precision recall curve is doing, is every point on this curve is a different decision threshold for someone who's trying to decide whether or not to investigate further a point that may be fraud. If I choose a point way up here, I don't have to waste any time on transactions that are false positives, but at the same time, I'm just not catching very much of the fraud. The recall is the fraction of fraud that you are catching. So you definitely want to be over here as much as possible, and you want to be up here as much as possible. So it does look like this particular model has a very sharp bend where there's one point that the F1 score is clearly maximized right here, and then it just suddenly plummets down. But if your fraud investigation division has enough resources to go after some of these cases, maybe it's useful to be able to catch a few more fraudulent cases down here at the cost of sifting through all these ones that are lowering your precision. Even at this point here, if you imagine you have 20% precision and yeah, well, let's say 20% precision and 90% recall. This is a data set. Remember, the validation set has 45,000 points. So 90% recall on the 78 fraud points there. It means you're only missing about 7 or 8. You have 7 or 8 false negatives in the entire data set. So you're catching 70 fraud points here, 7 or 8 false negatives, and at the cost of how many investigations of false positives? Well, you have a precision of maybe 20%. So that means 20% of the transactions you're calling positive are positives. You're only getting about 300, 400 false negatives or false positives in here. So not too bad out of a total data set of 45,000. Even operating at a point way down here means that you're only doing further investigation on another 1% on 1% of the data. So there's a few different options for the random forest classifier. You can do a balanced classification. And what that does is it actually, each tree that gets trained on the data, one of the disadvantages of what we did previously is if you have a highly imbalanced data set, each tree is only going to get a very small number of fraud points to build a model off of. So class weight balanced forces stratified sampling within the random forest model. And so running that one, this actually produces somewhat worse results for AUC, although notably the worst performance occurs up here in the region that you're likely to investigate anyway. And it actually improves performance down here. In every one of these curves, just to be clear, the blue line will always be the new model, and the black one will be some previous one that we've seen. For now, the black line is the random forest, the base random forest model. Another thing you can do is instead of just balancing the sample sent to the trees, balanced subsample, what this is doing is actually doing a balance at each possible split within the tree. So once you get down to a fraction of the samples at each node of the tree, it's saying to balance each node, I believe. Let's see. So again, pretty similar. Actually, a slightly better AUC. Again, it's worse than the base random forest model down here. Better than the base random forest model in this region. There's a lot of other stuff here. I don't think I want to take all the time to go through all of this. So another option, this particular model didn't do as well. I didn't investigate further how to fix that. What do we have next? Variety of data. I think I'll skip down to the section where we start looking at SMOTE and data augmentation.
Mm-hmm.
So that's right around here. So SMOTE, synthetic minority oversampling technique, something or other, is a technique that you can use with numerical data sets that are highly imbalanced. And the idea is that if we have points such that we saw originally, where you have many points in one class and very few points in the majority class, or very few points in the minority class, maybe it's helpful to generate synthetically new points in the minority class that are close enough to existing examples that we think, well, maybe we should be classifying them as fraud also, but it provides some new looks for the classifier to see. This is very analogous to, for those of us who went through the TensorFlow in practice course, very much like the image data generator, where we did data augmentation, where we took different images and just for training purposes, decided to rotate the images, flip the images, change the color balance in the images, stuff like that, just so that we know it's still a horse or it's still a dog, but we're giving our classifier something new to look at and hopefully helping its ability to generalize. So what we're doing here with oversampling is we're taking a data set that had only 315 training fraud points, and the default argument for SMOTE basically says, let's scale it up and produce a whole bunch of synthetic points so that now we have an equal number of points in each class. So instead of having 180,000 training points background and 300 fraud, now we're going to have 180,000 that are labeled as fraud. So let's see what the data set looks like. This is a little bit of a confusing visualization here. This is not looking at the SMOTE data. This is the original one, and it completely belies the true imbalance in here because we have put the red points on top and the black points are mostly all clustered on top of each other in that huge blob. But this data set has the original class imbalance with well over 99% in the background class. Here is what our first stab at SMOTE is doing. What SMOTE does is it says for each point in the minority class, look at its nearest neighbors and do some interpolation. Let's make the assumption that here's a point, its nearest neighbors are maybe this point's nearest neighbor is that point. And so let's generate points between these two on a line and add them to our data set. So you'll notice that it's only really looking at nearest neighbors, like we're not taking this point and that point and drawing lines between them and incorporating them into the data set. We are only really looking at drawing lines in a nearby sense. But now that we're looking at the red points or minority class points on top, it looks a little bit imbalanced the other direction. And again, this is not true. The number of points is the same in each class. So I will say I haven't been monitoring the chat. Are there questions I should be answering here?
Nope. We might want to mute SHE.
Yeah, please.
Here, okay. SHE.
Thank you.
Okay.
Thank you, Robert. This is very, very useful. I want to be respectful of everybody's time, and maybe if you don't have anything else for us, hand it over to David.
Yeah, let me wrap it up pretty quickly then. So I looked at a number of SMOTE models. There's a couple of different ways that you can apply SMOTE. Looked at a few of those. The main differences being a naive SMOTE that I just showed, and one that specifically chooses points near the borderline and focuses on those ones to augment. That is what you'll see down here, I suppose, borderline smut. Let's see. And then at the end, I tried a gradient boosted trees model, which gave me my best validation performance up here around 90%. But looking at the test set, quite a bit worse. Not completely sure why, because we didn't do a ton of tuning. So I'm curious to see what others found with differences between validation and test, if they used the validation set as put forth in our original coding shared on the Slack channel, which I think David provided. So this was just the results that I got, the validation shown here, and I threw them into the test set as well at the end. Turns out the single feature one actually does a lot better on the test set than it did on the val set. All the other ones are doing quite a bit worse on the test set. So I'm curious to hear what other people have done.
Cool. Thank you, Robert. Thank you for summarizing everything at the end. That's very useful. If you don't mind making David host, in the meantime, if you have any questions for Robert, now is a good time.
Can you tell me how do I do that?
Click on David's video.
Make host. That seems self-explanatory. Yeah.
Am I good? Yeah, it says you're a host. Okay.
May I ask a quick question? I may have missed it. Was there a chart showing the dollar amount for those 492 fraud points? Are they all small amounts, or some are small and large? Like, what's the distribution like?
So there was a chart showing that the distribution was
Just for the fraud points, not for all transactions, specifically for the fraud points, because when we miss some fraudulent transactions, you know, small fraud amount maybe not as critical as large, although they could run in sequence.
right. So there was not a visualization for just the fraud points, but there was one that had fraud points in different colors, in a different color than the background points, so you could see which points were fraud. There were some interesting structure in there. There were a lot of transactions fraud that were very close to a dollar. We discussed briefly why that might be the case.
And the other one, I joined a bit late. Was there a chart showing the time difference between different fraudulent transactions? Because more often than not, what I should say, in some cases, there may be a sequence of 5 transactions for the same card for the same poor customer, and those identified later as all being fraudulent, and they typically occur.
Yeah, you can see that in one of the visualizations that I showed early. I don't think
some of them were on a diagonal, so that's was made me wonder.
Yeah, one of the visualizations I showed at the very beginning had the index, which is kind of a surrogate for time, against the certain features where you could actually see clusters. If you were late, maybe you can go back and we'll put the video of this entire meetup will be posted to the YouTube channel, I think by tomorrow or Sunday.
Yeah.
So,
The one that I think I saw had a mix of fraud and non-fraud points, but not just the fraud points by themselves, which would make it more apparent. Because as David indicated, there is no column corresponding to card account, but if you were to look at the time difference between those fraud points, you may be able to link them to the same account that turned out to be.
yeah, that's kind of what it looked like looking at those points on that visualization. You know, there were a little bit of a spree in the middle of the night with a whole bunch of similar transactions all labeled fraud.
Thank you.
Great. Fortunately, we won't have much more time for any more questions. So please, if you have any questions, chat us or join us on Slack, and hopefully next time we can get back to you. I'll hand it over to David now. Thank you, Robert. Thank you so much for that detailed explanatory analysis and trying out different models.
So I'll try not to repeat a lot of the things that Robert went over. He did much more thoroughly than I could anyway. But you know, I will talk about the data a little bit at the start. One thing that bothered me a lot about this data is that it is the result of of a primary component analysis. All these variables are PCA. And they actually, a lot of times when PCA is done, the first thing you'll do before you do the PCA is scale all of your features so that you're doing your PCA with everything being at the same scale. I went ahead and made the assumption to see how it would result, what results I would get if I assumed that all these V1 through whatever functions were scaled prior before they did the PCA, so they're all scaled. They look like they're all in the same scaling, so I thought maybe that's true. One of my concerns is that when you do that scaling up front with the whole data set, and we're trying to create a validation and a test set out of that, we're introducing leakage, right? So that was a concern, but I'm just going to assume they did the scaling at the very beginning. Normally, we would only scale on the test set and do our transformations against all three sets. But with that said, I went ahead and, because I was going to do deep learning, I went ahead and did scaling against the amounts of the transaction and the time to bring them into what I hoped was a similar scaling with what they had done with the PCA, although I don't know what type they used. So that's where I started. I did the splits as everybody talked about at point 2. And then I'll skip down. I captured for later on, as you saw, Robert did class imbalancing. Sometimes you have to do a little bit more manual with some of the other non-random forest approaches, but you need these, counts of negative and positive, and I wanted to capture that up front. I created some helper routines to print out metrics that I wanted to look at. In this case, the true positives, false positives, true negatives, and false negatives. So I just created some helper functions. So we'll skip by all of that. And then I'm going to print out those metrics here in detail. So baseline, I went ahead and played with random forest classifier. I didn't spend a lot of time on this trying to optimize it either. I wasn't interested, but just for comparison purposes. And I ran it against the set with 100 estimators. And I got around I'm evaluating against the test set. So here I got about 70, and I was looking at Robert's values, and it's pretty similar actually what he was seeing. But so 71 in there. You can see from the metrics, I won't go through these because I have some nice plots at the end too much, but for this first one, I'll say I got, your true positives around 74, you missed 24 of the positive, and you did very well, and it did very well in the true negatives. It didn't do, it's very imbalanced, and it basically went for the true negatives. Next, I tried an XG boost. It's a very similar setup. I didn't do any, attempts at trying to optimize this. I just wanted to do it for comparison. So same kind of setup. It did a little bit worse with this, unbalanced data set just right off the bat. It's getting 65. How did it do a little bit worse? Well, it got a few more false positives, and it missed one more, fraudulent transaction. So not a lot of difference there. Then I wanted to do what we normally do, which is a neural network. I'm going to basically, I didn't do a lot of optimization on this, but I made it good enough, I think, to do a decent job. It's just a basic DNN, nothing special. I do a little bit of dropout and batch normalization. I capture in here when I'm printing out for each epoch the AUPRC as well as AUROC. And you can see this is a pretty small network with only 22,000 trainable parameters. So I'm going to run this and save my best model along the way, which I'm going to reuse later. I'm going to do 200 epochs, but I'm going to do early stopping when what I would call the competition metric stops improving. So you can see it starts off pretty well. It's at 75 on the validation, and it's up to, at the end, it's the best it got was 82. That's for the validation. Just apply. You can see it converges pretty fast. There's not a lot of overfitting, which I was happy with, and it's pretty smooth. It's not that unstable as it's training. So again, we saw 82 now in the test results. So this is my baseline DNN model, and we got 82 on the test. Here we're getting, I'll compare these things later, but we're actually getting more, a good amount detected. We're still missing quite a few, but we're not getting many false positives. So just comparing them, you can see it did slightly better. Our DNN model did slightly better at true positives. But remember, I didn't spend a lot of time optimizing random forest or XGBoost to do well. I'm going to skip ahead. As Robert explained, class weighting is one way to attack an imbalanced data set. And I did this with the random forest, similar to what he did with balanced. That actually seems to have hurt my results. I think I had a 70, we'll look later on, but it actually didn't improve anything for the random forest for me. For XGBoost, it also didn't improve it. It actually, I think, hurt that too. In both cases, I think is because it gets basically the same job of detecting the true positives, but it worsens the false positives. With a DNN, you can do this with class weights in your loss function. And the way you do that is I calculate the class weights here. Basically, if you recall, when I was tracking the number of negative and positive classes, I'm going to balance out, one for 0 and 1 for 1. You can see that's a huge imbalance, right? 0.5 is the class weight I'm going to use for the non-fraudulent transactions and 289 for the fraudulent ones. So, and I put that right in here where I'm doing my fit to tell it to use those. So again, running with the same thing. The best result I got when I did this was 0.71 on the validation, which is worse than what I saw without class weights. And here you can see there's a little more overfitting, but really what you're seeing is a little bit more instability that comes in from doing this in the training. Regardless of that, on the test result now, we're getting a much worse result, 0.71. And it's really because of the number of false positives. We actually have improved, we almost have half the amount of ones that we were missing as far as true fraudulent transactions. But at the price of getting a huge amount of incorrectly detected legitimate transactions that we labeled as fraudulent.
Yeah, and that all goes back to, what exactly are you trying to optimize here? Maybe
Right.
AUPRC is not always the right metric depending on how you're going to use the results.
Right. So the way I kind of looked at it is we improved on our recall, but we got much worse on our precision, especially with the neural network. So my next approach for dealing with the imbalance of our classes was to undersample the majority class using a random approach. So basically I'm going to take all of those non-fraudulent transactions and I'm randomly going to select a number so that I balance out. You can see in the original balance, when I print that out, we saw that before. This is for the training class. We had 15 frauds and a whole bunch of non-frauds. When we apply this random undersampler, it's going to give us a nice balance class, 315 in both. So I'll use that result and run it against my, for training against my my random forest. One thing I did at this point was I had read a little bit about applying kind of random forest as a feature importance as to how it got its result, what features it considered important. Was that it was important to do this with the balanced classes. So when I did that, I can see the differences in what's important. The scaled amount ended up being pretty important. Some things are pretty unimportant. Time was not that important. V9, let's see, maybe V7, and I think V14.
Yep.
And I don't know if that corresponded to what you saw either, Robert.
That V14 is the feature that I singled out.
Okay, so that's reassuring that I'm seeing very similar type of results with this distribution. But I don't know if this is a function of I got a very bad result.
So actually, I was just looking at that, and if you go up,
yeah,
I think what might be happening here is that this random undersampler is actually reducing the data set, and you're getting that same small sample is being selected for each tree.
Even when I'm doing the prediction?
I think so. I think the trees have been trained all. What you want to happen is each tree to get a different sample of the data, right? To have a balanced sample, but a different one.
Yeah.
You want the trees to be, I mean, they can be weak learners, but you want them to be as decorrelated as possible.
Right.
And I think what it looks like, and I couldn't get this to work right. I tried to build a pipeline to do this, and for whatever reason, because it used a fit resample method instead of a fit transform method or something, I ended up having to kind of do it manually. But I think what's happening here is like X train, Y train equals Russ fit resample. Now X train, Y train are real small.
Well, they are supposed to be small, right? They're supposed to be 315 and 315.
Right, but if you're then doing 100 estimators, all we're using just those same 315 points.
I see. So you're saying should have used a different number of estimators, probably.
Well,
right?
I think you just want to make sure that you're not using the same few background points for every tree.
Right.
And I think this is probably the same problem that I ran into, and so I'm trying to do it manually instead. But there's got to be a way that the pipeline actually works. I used this as an excuse to go back and play with scikit-learn for the first time in a while. So maybe somebody out there has a better answer to that. I hope.
Yeah, I'm curious. I'm not an expert in trees as well, but it looks like what you're saying, you want to shuffle your data every time you run it through a different tree.
Yeah, I mean, the whole idea behind ensemble models, especially like random forest in particular, is that you've intentionally made each tree weaker, right? By limiting the number of features it can see and by playing with and limiting the number of samples that it can see.
Right.
And what you're attempting to do by doing that, even though you make each tree a worse learner, if you can decorrelate the trees so that each tree gets different results, then it actually generalizes pretty well. Much better than a model that might be your best decision tree. So Dmitry here is suggesting changing the random seed. Maybe, although I think this is just a single call to classifier fit.
Yeah.
So I don't know.
Yeah, it's not. So I'm not surprised given the fact we reduced the data set to such a small, number of samples that we're not going to get a good result. I don't think undersampling is necessarily a great approach here. So same thing with XGBoost. I did the same thing. And again, no surprise, it's going to really detect a lot of legitimate transactions as false positives. What happens in our neural network? Well, again, using the same thing, it trained a lot longer, but we again got not the best result, and because it's such a small, we're seeing a lot more over fitting. with a smaller data set, and just not a great result either. Again, same problem, lots of false positives. So let's go on and try something else. I tried another undersampling approach called near miss. It's instead of just randomly taking out some of the ones, this tries to do a little bit smarter way of pruning the minority class and trimming it down. We can look, again, same kind of problem probably with random forest, and with my deep network, even crazier results, just no good at all. And so again, a very high result of false positives. So so for me anyway, I didn't get any good results with undersampling. So then I tried oversampling. And SMOTE is a very popular one. There's another very, very similar one called AdaSyn. It's another synthetic one.
We have a question here that may be relevant right now from Virop. Yep. What was the batch size? Having a small batch size might exclude the minority class from a batch.
It could, that's right, yeah. And I did need to reduce the batch size some for this one. So I went down, I think, to 8, which could very easily have created that issue. And that probably would have shown up in a lot of instability, which is kind of what you might attribute this to. So, yeah. Definitely undersampling was not my my best approach. Oversampling.
But for a neural network, I would think that having, some batches that don't have fraud examples is probably okay, because you're just continually readjusting one set of weights.
Right. So then I thought about, well, oversampling. Let's see how we do there. Again, this is just an alternative one to SMOTE. Ended up with very close amounts of fraud and non-fraud when it applied. And random forest, pretty much the same result I saw before. It didn't really improve it much. XGBoost, I had a problem. I don't know what exactly. I didn't investigate this much, but you can see it really didn't like this data set as far as predicting false positives. So I'm not sure. Maybe it just the way the synthetic points are built with AdaSyn, it just identified them as being. I'm not sure what happened. Someone with expertise in it probably could tell us a little more.
So, I mean, if I recall, the AdaSyn does, it samples kind of inversely to the density.
I believe, yeah.
So I think I looked at it and was thinking that because there are so many places where the density is low, it might have difficulty.
Could be, yeah. I took
further.
This site where I got this imbalance package, they have some really nice documentation where they show some plots and how each one of them, where they add the new points or where they remove them if you're doing undersampling. And I thought it looks similar to our data set, but it just didn't work apparently. So there's a million other different ways you could do it too. So I'm not sure what was the best. You could do a nice long study on oversampling, undersampling methods. For our DNN, it didn't do too bad. I mean, it's getting 65 on our validation set, which is not that great. What I thought was interesting, it's quite a big gap here, which surprised me. It's overfitting, even though we balanced it so much. So 65 is, again, not very, very good. Where did it didn't seem to improve on its ability to detect the fraudulent transactions. So our oversampling method, didn't do a good job. So maybe that's not to be expected with AdaSyn. Now there are several methods where you can do oversampling and undersampling or cleaning methods and combine some of these as a combo method. One is called SMOTE, ENN, which SMOTE is, as Robert said, the way of doing the oversampling with synthetic minority oversampling technique. And the cleaning is a technique called edited nearest neighbors. If you have any, you want to go into detail of that, I encourage you to look up the documentation for it. But so I thought I'd try Smotine. And then my balanced data set is now pretty big still, right? So it's going to give you the large size. The random classifier result was not improved. The XGBoost was actually did pretty good on getting more true positives, but at the price again of false positives. So I'll show you. I mean, my deep neural network, I would say sort of liked it, but not a lot. 75% is below what our baseline was. Again, a big spread between the training and it almost perfectly got the training, right off the bat. But again, it's having problems with false positives. So I wanted to look at a summary of this. It turned out our best result for me was with the baseline dense neural network. However, I got the best recall when undersampling, which is not surprising because you're giving more, and I'm just talking about my DNN model here, but I get the best recall with undersampling, which is not surprising because I'm now focusing on those fraud charges. But the precision is going to go down, and Robert had some great plots to show that. So again, in our test sample, just to remind you, we had 56,000 non-fraud and 98 fraud cases. Here is the AU PRC total percentages for my different results. Again, the green is in case you can't read this, the green is the dense neural network, and that was my best result, was on the baseline there. The random forest is the blue, and other than the undersampling methods, it didn't change a lot when I tried different methods. It was pretty consistently just above 70. XGBoost didn't improve much, didn't change much until I tried to do oversampling or undersampling, and none of that worked. And I think people probably have a good indication as to what it did wrong or why it doesn't work there. Probably the thing that maybe people care about the most in an organization might be the true positives. And if that's all you cared about and you had infinite resources to eliminate all the false positives, you could get actually the best results with this undersampling near miss for random forest and XGBoost, and for undersampling randomly, the dense neural network did its best in that case. The false negatives are the ones you missed. Again, the lowest result is when you're undersampling, you're going to get the most. And here's the problem, of course. What you pay for when you do, you're going to get a lot of legitimate select actions incorrectly classified when you're undersampling with some of these. That's probably just the way I did it. So this may not be. There may be, as Robert said, a better way to balance this. And then that's the summary. So that's. Any questions?
Yeah, David, I had a couple.
There's a couple in the chat. Yeah, Viraf, do you want to ask those?
Yeah. So did you try different loss cost functions? Like you talked about focal loss some time back on one of the channels, Slack channels. I haven't found it useful, but did you?
So I've tried focal loss on quite a few different type of scenarios like this, and I haven't found a lot of difference. So in this case, I stuck with the binary.
Okay. And did you try changing the threshold?
What's that?
You change the threshold?
In the focal loss?
No, just in your outcomes and your results. Just say if you're changing the threshold, basically, I think they use 50% or 0.5 as to, so whether it's positive, negative. So if you change the threshold, you can move, basically shift more from one side to another. You'll also get more noise at times, but I was wondering if you tried shifting the threshold.
No, I know what you're talking about. So in the particular Keras metric for these, it's actually using the probabilities.
Right.
The AUPRC metric is kind of agnostic towards threshold. It considers the entire curve.
Right.
Okay.
But certainly these individual precision recall and F1, some of these plots at the end here do depend on threshold.
Right.
Thank you. So what is the F1 score that you got on this?
I didn't actually.
I don't think he actually showed F1, but F1 is just the harmonic mean of precision and recall.
Yeah, but I was wondering if you had something.
I did not run it on these.
No, I think I just said that without actually seeing it on the slide.
Right, thank you.
There's a question about one new layer they introduced, David, the exponential layer unit, ELU, in your DNN.
Oh, sure.
Is that just a scaling layer? What exactly? I think I quickly.
So ELU is an activation function. It's not that different from ReLU. It's called the exponential. What is it? What does the LU stand for? Anybody know?
Linear unit?
Yeah, it's exponential linear unit. It's the name. It's a slight, for a lot of problems, it's a slightly improved over ReLU, but I don't think it makes any difference in this case. Just something I was trying.
Yeah. And the other thing I want to notice is when I tried doing this, I did not scale amount and time, and I went directly with the DNN, and I was not getting any good results at all. And I look at your notebook that you were scaling time and amount, but once I did that, like immediately I got much better results.
Yeah, I think our neural networks are going to be really sensitive to that. The random forest and XGBoost, probably not. But
yeah, it's a huge difference.
Yeah.
Any more questions for David before we ask Dimitri to share his notebook with us?
So I have a question. When you try to introduce new samples, have you also used the time? Kind of like, I mean, I kind of don't really see the value of creating fake time samples, you know, and I'm wondering if that kind of was one of the reasons why the results were worse. I'm not sure if it makes sense, you know. Like I was looking at the values that you had, you know, you have a vector of 30 values, and one of them is the timestamp. What would be the value of creating fake time points?
Well, you certainly could remove time from this, or
yeah, maybe that would improve, because I mean,
yeah, I think, you know, I would hope that especially with a deep neural network that is smart enough to eventually figure out that it's not important, and not pay attention to that. That's what you hope with most neural networks, is they learn which features are important and which aren't, and they weight down the ones that aren't. But most of the what you're thinking about is oversampling, where you're introducing these synthetic points, and you know they're usually looking at all these different axes and whatever, if you think of the feature space, and they're doing some algorithm to introduce new points that are logically similar to the points that are already there for the class that you're trying to oversample. If time is not that important, then anywhere that, you know, whatever it assigns time, there's going to be not a problem, right? So if you're introducing points with any kind of time, this shouldn't matter, right?
Right. Yeah, I mean, that's a hope. Yeah.
Yeah.
So, I mean, the only time in which you would expect these synthetic techniques, especially ones that rely on convex combinations, basically linear interpolation between two existing points, are cases where your model based on the original class balance is going to generate curved decision boundaries when you actually don't want them.
Right.
So maybe the classic example of that would be some kind of highly imbalanced problem where you try to fit a support vector machine and a radial basis kernel or something, and you just end up having a decision boundary which is like little spheres around each point. Those are the types of situations that you want to avoid by using SMOTE. So I can't think of why time would be specifically a variable that originally would have generated curve boundaries that you don't want to interpolate between, but I really don't know.
Mm-hmm. Okay. Yeah, thanks.
Sure. So I'll stop sharing at this point.
Please, can you make Dimitri host?
Yep. Let me share my screen.
Let me make you host. Hold on.
Oh, thank you.
Okay, you see it? Should.
Yep.
Yep. Okay. Can you see my screen?
Yes.
Yeah.
So my motivation in doing this exercise was actually exploring the objective, the metric, because there was quite some discussion about AUC versus AUPRC, and what the right metric should be. I just did a quick research on true positives versus false positives for fraud detection, and basically the objective of the whole exercise is the finding the optimal sensitivity of the filter, right? Because you can classify everything like fraud, and you can just do nothing, and those are the two extremes, and you have to find the right point in between. And so the question for me was, how do we quantify that right point? And so this is the formula I came up with just for myself. Basically, what it says is each true positive, meaning correctly identified fraud, saves you, the merchant, this much. Basically, your cost of that item, and saves you the chargeback costs, which sometimes are very big, like 15 euros, 20 euros per transaction, etc. But also, false positives actually cost you too. So you lose the margin that you could have earned on that transaction that didn't go through. And so there is actually quite a lot of discussion about the false positives being actually more detrimental for the business than the true positives. And some merchants go, they just psychologically avoid a fraud at all costs because they don't like the chargebacks, etc. And they end up losing a lot of legitimate business, which is, the filter cuts off. So finding that optimal point was actually interesting. And so I started with these economic assumptions. It does depend on the marginality of your business. Like if your marginality, if the gross margins are very low, you can afford, losing a lot of legitimate business, so your false positive rate can be high. But if your margins are big, like 50%, 60% margin, then recall is much more important. So I just assumed these parameters, and then I didn't do much of anything different than David and Robert showed. Basically, also explore the class imbalance. One thing I thought would be great to understand is how much actually, what is the actual economic cost of that, of the fraud. And, the total transaction amount is 25 million euros. And the cost of fraud is only 60,000. So relatively speaking, it's not a huge amount, but, someone asked the question of, how big the transactions are. Percentage-wise, the amount in the dollars is bigger than the amount in the count. So fraud is on average slightly larger. So then I did the log transformation as our colleagues, and then I just went to visually describe the features, and basically put all of them into this distribution and violent plots, just to understand what's the difference between good and bad. Like, for example, this is the time, and we can see this is a nighttime. I think this is the legitimate transactions are low, and the bad transactions don't seem to have that deep, probably international fraudsters, whatever the effect may be. And just by looking at these transactions, you just see and just the variables, you see some of them have a very salient sort of differences between the good and bad classes. So just off the bat, we could see the classifiers should probably work pretty well, which was the case. Like we have the V14 that Robert described. Like V14 is hugely different between good and bad. V16 I think is also, etc. So many features are very informative.
Dmitry, I'm curious about your experience with Seaborn here, because I actually attempted to create a couple of these with Seaborn, and it ended up taking a long time on my machine, and I just ended up just choosing Matplotlib because it was fast. Seaborn took a long time to render, so I'm wondering if you had that experience, because I love the way these look. This
takes probably a second byte per chart, not more than that. Okay. Seaborn is I think is on top of Matplotlib. It uses Matplotlib API. This is the amount. I think someone also asked, the distribution by amount. You can't really see here, but the legitimate transactions go up to 25,000 euros, and all the fraud is, probably, below 100 euros or something. The scale is not quite right, but then I just went to visualize the correlation with the class, and we can see, there's this group of until V18 or something that actually does have very high correlations, and then there is a group of features not really correlated. So my instinct was, let's try to remove the weakly correlated features and see what happens. Maybe just introduce noise, and we will just get rid of them and the performance improves, but it doesn't. So there is still some information in the weakly correlated features, just tried empirically. I went in to test the significance, and try to remove those that are not significant. Didn't work. And then I split the same way, so 20% test. Didn't do the validation because the fraud class is already in thin space, so I thought maybe just cutting that further isn't worth the effort in this particular case. Tried visualizing with TSNE. Again, just confirms our intuition that the classes are very well separable. This is a nice picture. A bunch of helper functions, and so then I went on and just tried, I think, 4 things: logistic, SVM, XGBoost, and neural network. And for within each class, I took a parameter that could have affected the performance, I think, the most. In this particular case, this is logistic. This is just a C regularization term. and the regularized curve works better. And I think coming back to the metrics, so what I did is I added to each plot, I added the point that corresponds to the maximum gain. So the maximum economic point is this purple dot over here. I could have probably spent more time and plot the contour lines for the economic gain, but didn't have time to do that. So this is what it looks like. Basically, this is the best point on this line, and that tells us already something about the relevance and applicability of area under the curve, because in this left part over here, the curves could have looked different, and some may be higher and lower, but it doesn't really matter because the optimal points are in this corner, just as you had, Robert, the very kinky corner in that part. So nothing surprising here. Is just the AUC here and AUPRC are not very telling. That's, I think, the main conclusion from it. The same thing with SVM, same pictures. And XGBoost, I just had these parameters, from one of the previous exercises I did, and they seem to work good. I just played a little bit with the subsample ratio, and this is the picture I got. And again, this is a good example. Like the area under the curve is clearly better than for logistic, for example, but this left part, for very low recall is basically irrelevant because the model does not tolerate low recall. Yeah, this is again along the same lines, the feature importance and the same V12, V14, V17 that you guys had. So again, confirms all the intuition. With neural network, I didn't do as much tweaking and optimizing, just tried a very simple one. But maybe I should, but this is what I got. Lastly, I tried autoencoders. I just saw people doing exactly that on Kaggle. So I thought maybe I could extract features through some autoencoder network and then use those features to put through XGBoost or something. Basically, long story short, it didn't work. So this is the t-SNE embedding before. This is the t-SNE embedding after, just to visualize. And it seems like they're pretty well separable. But if you look at these fraud points, they are still part of this green cloud. So it didn't really separate the false negatives. So these are the bad guys, the false negative, the red dots. They're still part of this big green cloud. And it didn't work. Maybe it's a parameter, hyperparameter optimization issue. And so finally, I just took from each class, I took best in class classifier and put them all together. And probably it's better to look at the picture. So it looks like this. So XGBoost beats all the others, which are inferior to them. And again, the same thing, XGBoost has a very nice area here at the left, but pretty much if this purple line was just continuing horizontally, this point would be still the optimal point. So that's what I did. I was amazed to actually see that the basically how good all of the models work. Basically, from 56,000 samples, you are left only with a dozen of false positives, false negatives. So this is very close to a perfect optimizer, or close to perfect optimizer. And I sorted them, so I optimized them with this maximum gain thing, which is basically the percentage of a gain that a perfect filter would have. So if you would devise a perfect classifier that would sort out all the frauds, and false negatives, false positives will be 0, you would have like 60,000 euros saved. And with this classifier, you would save, 62% of that theoretically possible savings. So this is what I did. Maybe, I should have spent more time on the neural networks and potentially onto encoders. But yeah, if there are any questions, please go ahead.
Dimitri, on a lot of them where you're using the same model, but you were changing the parameters and seeing how the results changed, it seemed like your economic cost, the best economic gain, I guess, that you showed,
Mm-hmm.
seemed to be in line with what AUPRC was also showing.
Yeah.
So they seem to be so, I mean, I guess does that kind of give some credence to AUPC being the right metric?
Well, if you look, well, most of the time, yes. But like if you look, for example, at this logistic and SVM, like SVM is better in the maximum gain, but worse in the AUPRC.
Right. I didn't mean between different models, which I think I see your point
within each class.
But within a model, it seemed like it might be.
I think within a model, as far as I remember, within a model, AUPRC was a good indication of how good it was economically. Yeah.
But not necessarily between the models.
Yeah, but not necessarily between the models. Yeah.
Okay.
Mm-hmm.
Since I missed some of the intro, why did you all use AUCPR versus F1 score?
F1, well, F1, I didn't use F1. F1 is a harmonic mean between precision and recall.
Right.
And you could use that. It's just the question is whether it tells you the right thing, whether it's the right answer to the question you're asking. And I thought neither that nor AUPRC is actually answering the question that actually we're interested in. So that's why I spent some time, researching, reading some articles online as to how to optimize that sensitivity of the filter, and came up with this economic gain thing.
Because my understanding was F1 is a good metric, as is AUCPR for imbalanced data set.
It's an aggregate metric. It's a metric trying to tell you, both recall and precision, but it has a specific formula, right? And that formula may not be your objective function.
Right.
But it's also my understanding, right, that we use PRC versus F1 because this is highly imbalanced data set. Is that the main reason?
No, that would be for the AUC, certainly, the area under the curve or the rock curve. That you don't use for imbalance. That needs, but the AUCPR is fine for imbalance, from what I understand, as is the F1. And so I was just wondering, going back in history, because I didn't follow your Slack discussions where you all made that decision, just because I might be missing something, why did you all select one over another?
So I think Dimitri did a great job of analyzing what might be the proper metric to choose. We chose it because that was the Kaggle suggested metric for evaluation.
Hi, thank you.
AUPRC. Yeah.
Okay.
Yeah.
Any more questions for Dimitri? Dimitri, by the way, your notebook visualizations are beautiful. A lot of people are commenting on chat.
Yeah. Thank you. And also for taking that objective function and approaching it slightly differently. So thank you.
Okay.
Cool.
I have a question for you all, slightly different. Do you all run it through some AutoML tool? Because I typically just throw my data at an AutoML, try to figure out which algorithms are doing better, and then I start moving forward and trying to optimize and see how far I can go. So did any of you try that?
I did not.
No.
No.
That would be interesting.
Yeah, maybe you can give us.
I started it, it's running, unfortunately. I started it when this started, but it's still running. It's
But
done.
we like to discuss these things well after the the facts, so please keep us informed.
Yeah, that's fine.
We're still going back to our first coding challenge and talking about it.
Dimitri, do you mind making me a host, please, so I can share my screen? And yeah, keep the questions coming. Thank you, Dimitri. Just click on my video and make host. I still have a little bit of catch up to do on all the coding ones. Like, oh, I should have done this, I should have done that, I should have explored this, I should have explored that. But this is a new challenge for me. I'm not an expert in XGBoost and all that. I've heard about them. I haven't really used them. So this was a very good challenge for me to see the machine learning and the deep learning part. Usually,
other thing is I found, although they're meant to be the same, I found light GPPM to be slightly better on some of this stuff that I've done than XGBoost. So I don't even look at XGBoost now. So that's something else that maybe to look at.
Yeah, and usually you hear in structured data that machine learning solutions are usually better than deep learning. So I'm glad that I'm just curious to see the results here. That usually DNNs kind of outperformed other solutions, not universally, but in many cases. Cool. So these are just some slides that we saw. The only thing that I added was just a correlation plot between the different features, all the different 30 features. And I just tried a very simple DNN with and without the scaling. And I saw the scaling made a huge difference for me. Cool.
One of the things I find so valuable is to see other people's ways of doing things, and you learn a lot from that.
Absolutely, absolutely. Yep. That's the whole goal of this coding challenge. Yeah.
Now I got to learn how to make those pretty notebooks.
Exactly. Yeah. Cool. If you haven't joined us on Slack yet, please join us now. If David or Robert, if you don't mind putting the link right now on Zoom. We're pretty active. We ask questions. We interact with each other. There's a coding sub-channel on our Slack channel. Yeah, you can join us there. Yeah, please join us. Having said that, I think the next session is either a happy hour or we'll have a presentation by another group. It's pending confirmation, so I'll let you know the moment that is confirmed. But after that, we'll be tackling a time series prediction task using weather data from Madrid. Again, we're encouraged to use both machine learning and deep learning approaches, whatever is your skill set, whatever you feel comfortable with. Our goal is to compare notebooks, look at how, as Robert said, different members approach this challenge, and as long as we agree on some kind of test training, test splitting, and some metrics, it'd be interesting to see how our models compare. Cool. So that would conclude the 5-week challenge. This is week number 4, and if you haven't joined us before, we have all our sessions recorded on YouTube, and you can also find the link on our meetup page as well. Any other questions or recommendations or feedback for today? So there's a lot of conversation on chat, so I'll try and save the chat, and if there's something that we want to post on Slack, I'll post that as well. Cool, a lot of thank you.
Sorry, I was busy trying to unmute myself. I did have a question for, I guess it was for Dimitri, because you had a really good result with XGBoost, I think, right? Or am I? Yeah, you had a really good result with XGBoost, but who was it? Who spoke earlier who didn't? Was it David or Roberts didn't have very good results with it? I was just wondering what you thought the difference was. Like, what did you do differently with it?
I haven't had time to go into the Robert's and David's notebooks to compare, but I think the XGBoost was already kind of fine-tuned because it was taken from another exercise, which also was a structured data set. It was a similar thing. So maybe I sort of spent more time fine-tuning XGBoost in the past than neural networks. So that might be the reason. But also the structured data sets that I came across, XGBoost is good exactly at this kind of data. There is nothing, no sort of complex features to extract. The features are right there. It's plain and simple. It's just finding the right decision boundaries in this 28-dimensional space, whatever, which is something XGBoost is very good at. I think that's at least that's how I explain this for myself, basically.
I see. All right, thanks.
Cool. Any other questions from anyone? I saw some other questions on chat. If you want, you can unmute yourself and ask them now. Cool. If not, then okay. Thank you, everyone. Thank you, Robert. Thank you, David. Thank you, Dimitri, so much for sharing your notebooks. I posted them on our slides as well as on our meetup. You can find them there. And thank you, everyone, for joining. This is a very interesting session, and hopefully we can take something and use it in our own projects. Having said that, we'll see you next week, and please join us on Slack as well as on YouTube.
Thank you, guys.
Thank you, everyone.
Thanks.
Thank you.
Good evening, and have a great weekend.
Yes.
You too.
Thank you, everyone. You too.
Bye-bye.